The material that we cover in Chapter 10 is a little bit different because we actually talk about measuring two different values and comparing them to each other instead of just one. So we're not just measuring people's heights, we might be trying to see the relationship between height and weight, for example. So that's going to kind of be the difference here in Chapter 10. So when we're looking at two values like that, we call it paired data. So paired data is when you're looking at two different variables about a particular subject instead of just one and looking to see if there's a relationship between the two. If there does appear to be a relationship or a pattern between the two variables, then we call that a correlation. And so we'll be doing correlation analysis to see if there's a relationship, and if so, how strong that relationship is. And then eventually we'll actually be doing a hypothesis test to see if that correlation is strong enough to extrapolate out to the whole population. We can have a positive correlation, a negative correlation, or no correlation. And the only way to really determine that is to look at a scatter diagram. And there are also some related calculations that we'll talk about how to do. So a scatter diagram, also called a scatter plot, is a graph where each dot represents one of the subjects in your study, and then one of the things that you measured about them is the x-coordinate and the other thing is the y-coordinate. So maybe I have a graph where each dot is a person and the x-coordinate is their height and the y-coordinate is their weight. And when you look at these scatter diagrams, you can get some sense whether it looks like there's a correlation or not. And in this chapter, we're going to be primarily focused on linear correlations. Do the dots appear to line up? And so these are three examples of what we would call a positive correlation. In the first one, the dots aren't in a perfect line, but they in general seem to be moving in the same direction and creating a wide line. And then in the middle we have a little bit stronger positive correlation, and then on the right that's a perfect positive correlation because it is perfectly lined up. And they're positive because as you go to the right, the dots are moving up. And then these are similar examples for a negative correlation. As you go to the right, the dots move down. There are some different cases where you would say that there was no linear correlation. This first one on the left shows really no correlation at all. The dots are just completely scattered all over the place. But on the right, there is a pattern. It just isn't a linear pattern. It's actually more of a parabola, more of a quadratic correlation. We will not be looking at that sort of correlation in this class. We'll only be focused on linear. But keep in mind that just because there's not a linear pattern doesn't mean that there's no pattern at all. So we can create scatter diagrams on the calculator. I'll walk you through this very briefly here. There are several steps to setting this up, so I will also come back to this in a calculator video as well. But the first thing is to go to Stat Edit and enter both columns of information because you'll know two different things. So you'll put the x's under L1 and you'll put the y's under L2. Then you'll need to turn on your plots. So you'll go to the second y equals. This will pull up the stat plot screen. And then you'll just hit enter to get into one of the plots and turn them on. So maybe hit 1 to get into plot 1, or just hit enter on it. And then this screen will pop up. Make sure that it's turned on. Make sure that in the type choices you've chosen the first one. That's the scatter diagram. You've been in this screen before for box plots actually, so make sure that you've got that changed to the scatter diagram option. And then make sure that the X list and Y list say the lists that you put the X and Y under. And then mark is just a personal preference. What do you want your dots to look like on the graph, so it doesn't really matter. And then once you have everything entered, you can hit graph. You may not see anything because the screen may not be set to the right values to see the dots that you've created, so you may need to go to zoom and then choose number 9. Zoom is one of the buttons right under the screen, and then zoom 9 will go zoom in on your dots. So like I said, I'll come back to that and show you how to do that a little more slowly in a calculator video, but if you're already familiar with the calculator, that might get you going on that. Just to put some numbers with this and see what a scatter plot actually means, let's walk through an example here. We've looked at some cars and we've measured the car's weight and its miles per gallon on the highway. So we're going to create a scatter diagram and look at whether it seems that there's a relationship based on that. So if you want to pause and do this on your own calculator, you can, but I've gone to stat edit, I've put the weights under L1, and then I have put the miles per gallon under L2. Pretty much you just leave them in the order that they were given to you in the problem. So whatever was given first, that's L1. Whatever was given second, that's L2. And then when you create the scatter plot, this is what you see. It's not a super strong correlation, but it does appear that as the dots move to the right, they do seem to be getting lower. So it does seem that as the weights go up, so that would be to the right because we've got weights on the x-axis. As the weights move to the right and get larger, it seems that the highway miles per gallon, which is the y value, seems to be dropping. So it does appear that there's a negative correlation where more weight means less miles per gallon on the highway. Now, like I said, this is not a perfect line though, and so we kind of need to get a sense for whether that's close enough to actually be meaningful. Is this a strong enough relationship to make any use of? And so there's actually a better way to measure that than to just look at it and sort of guess. There's an actual value we can calculate called the linear correlation coefficient. And we can find this on the calculator, and it actually measures the strength of that linear relationship between the two values. A little bit of notation here first. We use an R to stand for the linear correlation coefficient if we're talking about a sample. And then if we're talking about a population, we actually use a Greek lowercase r, which is a rho. It looks like a curly P. So be careful when you're writing that it doesn't actually look like a P. Make it a little rounder. I'm not sure why they chose R for correlation coefficient, but for both the sample and the population, that's what it is. Now, correlation coefficients are values that fall between -1 and 1. And it's actually bad to be 0 and good to be either direction away from 0. So 0 means that there is no linear correlation at all. And then as you go from 0 towards +1, the positive correlation gets stronger. And if you go from 0 left to -1, that means you have a negative correlation, and the closer to -1, the stronger. So 1 is a perfect correlation whether it's positive or negative. Either positive or negative, both perfect correlations. Just one has increasing y values, one has decreasing y values. We usually round these to 3 decimal places. And just terminology, I don't know if, statistics go with samples and parameters go with populations. When we're talking about R, which is what the calculator will find for you, that's talking about the sample. So going back to these scatter diagrams, this first one here on the left is a perfect positive correlation. You can draw a line straight through all of those dots. So that would have a +1 as its correlation coefficient. B might be more of a 0.9. They're really close to the line but not perfect. And then C is a 0.4. They're pretty scattered. So the closer to 1, the better. And if it's positive, notice that all of these, as you go to the right, the dots move up. And then same thing on the negatives, except this time as you move to the right, the dots move down. So all of the correlation coefficients are negative. So this first one is a -1, which is a perfect line, but moving down as you go to the right. And then a -0.9 is pretty close to the line, -0.4 getting farther away. And then no correlation at all. They're just all over the place, not really moving either direction as you move to the right. And so if it helps, some people it helps to see this on a number line. So 0's right in the middle, that's no correlation at all. Things that are close to 0 on both sides are weak, and then they get stronger as you move outward to the right and to the left. There's actually a couple of places on your calculator where you can go to calculate the correlation coefficient. So it's possible in an algebra class you may have done this with linear regression screens. We're going to do it with the linear regression hypothesis test screen because we're about to use that for something else anyway, so might as well go ahead and start now. So you go into stat tests and you scroll all the way down until you find the linreg t-test. On the older calculators, this is choice E. On some of the newer ones, it's actually been bumped down to F. So just look for linreg t-test. We're not going to talk too much about the hypothesis test itself just yet, so you won't worry too much about anything except your X and Y. Make sure that they're the correct lists, and then just go down to calculate. Don't worry about anything else just yet. When you calculate, a whole bunch of stuff comes up. If you scroll down all the way to the bottom, you're going to find R. And so that's what you're looking for. That's the correlation coefficient.